Hello and welcome to today's lesson in quantitative reasoning. We're going to look at some more truth tables for compound statements, and this time we're going to add the conditional and the biconditional connectives to our work. These students tend to find these a little trickier than the and or the or as far as evaluating the truth of a conditional or a biconditional, but hopefully we'll get some practice here and that'll add to the practice you get in your homework and you'll be good at it. So the notes I have here are taken from your text, and that's the copyright there. So again, truth tables for compound, conditional, biconditional. We've already talked about these disjunctions, conjunctions, and negations, and we haven't talked about a simple conditional statement except in class. We haven't done a video on that, and we haven't done the simple biconditional, and then we get into some ideas of some special types of statements where you get either all falses, be a self-contradiction, or all trues would be a tautology, and an implication is an if-then that ends in an all true. So we'll also get to talking about those here. So we've seen negation, conjunction, and disjunction, or negation, not and or. We took a look at that. And we mostly used two statements, P, Q. We had two statements in our compound statement. Now we're going to start talking about when we have three statements, which means we get 8 possible combinations of true, false. And that comes from the fact that if you had three statements, and they're usually P, Q, and R. Now, anytime P is true, Q could be either true or false. And anytime either of these pairs of cases happen, you get another pair of cases where R could be either true or false. So you can see that the path for just P being true ends in 8. There's 8 paths: true, 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 false, true, false, true, true, false, false. If I write the similar path for P being false, I'd get all the same Q's and R's. I'd have 8 paths when I was done. And that's from the idea of there's 3 simple statements. It's a base 2 exponential to figure out the number of rows, because P and Q and R, they each have 2 choices. They're either true or false, and you make one of 2 choices 3 times. That gives you the exponent. So for 3 statements, we're going to get 8 rows in our truth table. So this jumps in using or and. So that's the first extension we make here. Here is how you make a 3-statement truth table using or and. So I'm asked to find P or not Q and not R. So the way I know I have 3 statements is I just count the different letters. Now, if I had a not P in here somewhere too, I would still only have 3 letters, P, Q, R. They go in alphabetical order, left to right. Let me pick a pen you'll be able to see better. And our inputs, look at this, the first 4 rows. P is true for the first 4 rows and false for the next 4. And then when you split those 4 up, so you see here's your first 4 rows in Q, first half true, first half false, and then you repeat that. And then R will alternate, true, false, true, false. So here's your true, true, true path. Here's your true, true, false path. True, false, true, true, false, false. And then this block repeats for the same. So the way you remember to set these up, and they have to be set up the same way, is if you have 8 rows, alphabetical order, the first is 4 trues, 4 falses. Then you cut that 4 in half and do a pattern that repeats that many times. 2 trues, 2 falses, 2 trues, 2 falses. And then you alternate. The last one will always alternate. If you had 4 statements, you would have 16 rows. You would have another letter, probably an S. It would go 8 trues, 8 falses. 4 trues, 4 falses, 4 trues, 4 falses, 2, 2, 2, 2, 2, 2, and the final S column would be every other one. We're mostly just going to work with up to 3, with either 2 or 3 statements. So the bottom line for this is that you have to see that every time you have 3 inputs, 3 statements. This is what the first 3 columns look like, and the names of the statements are in alphabetical order at the top. That's a T. I've kind of crossed over it. But that's what your first 8, that's the first 3 columns. Your 8 rows look like that every time. Okay, so write that down somewhere. Have that handy. Every time you need a 3-statement truth table, you start like that. So let's look at this now. So P, Q, and R, that's just inputs. I don't even care what the problem is. I can write out P, Q, and R to start with. Now they want me to find this. That's pretty complicated. So I'm going to work from the inside out. First, I'm going to work with P or not Q, which means first I'm going to make a column for not Q. Then I'm going to make a column for P or not Q. I'm going to build on that. And then I'm going to make a column for not R, and then I'm going to make a column that ands those 2 things together, because that's finally what I want to do. But I get there a step at a time, as we'll see in the next table. So this is what I'm trying to show. So I see it'd be handy to know what not Q is, so I can do P or not Q. So not Q, you got to be careful here because R is right next to it. It's tricky not to accidentally write not R there. Q is over here, so true, true becomes false, 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 false becomes true, true. So and you notice the pattern for the input Q was 2 trues, 2 falses, 2 trues, 2 falses. Well, if I have to write not Q, I right away know I have 2 falses, 2 trues. It's just same pattern, but with the opposite letters. Now I have this column to work with to figure out P or not Q. So for P or not Q, I'm going to look at these 2 columns in green, and I'm going to look a row at a time. In row 1, I have a false, I have a true. The or statement, the order doesn't matter, so I just look, I have a false, true, or only needs 1 true to be true. Second row, there's a true there, so that's true. Third row, and the other thing I notice, I have a P here. The first 4 rows of P are all true, so it doesn't even matter what not Q is. As long as I have 1 true, the or is true. So if I did them individually, I'd find I have 4 trues, or I can just say, listen, P is a true, therefore P or not Q is true. Now here P is false in this 5th row, and not Q is also false, so that gives me a false right there. False or false, again, is a false. False or true is a true. False or true is a true. So that is this right here. Then I want to take a look at not R. Okay, not R. I make a column for that. Not R, so here's R. It's just the opposite. R starts with true and alternates, so not R starts with false and alternates. False, true, false, true, false, true, false, true. And then I am joining them, that with an and, P or not Q. Now it's in parentheses there, but it doesn't matter. It's the same thing. This with not R is what I'm anding together. So I found P or not Q by doing these 2 columns in green and oring them. Now the 2 in blue are what are being anded for my final result, and an and is only true if both are true. And I can look, these are right next to each other, so it's easier. So there's a true, there's a true, there's a true. Everything else must have had a false in it. So it's false, false. So do you have to go, one at a time? Well, after you go to that, you come up with some strategies. I tend to look for the trues on the end because there's fewer of them and the rest are false. And let me just double check. 2 trues, 2 trues, 2 trues, yes. So this final column here, this is actually my answer to the compound statement for the truth table. It has a whole column for the answer. Okay, so that's what we did in the last video, only with 3 statements. Here is another example. Oh, this is the same example. Okay, this is the same thing filled in. And let's make sure, I don't know if I go back and see it's missed. So I had a true in the 2nd, 4th, and 8th rows, and I had a true in the 2nd, 4th, and 8th rows. I did that correctly. But hopefully with my explanation, you can see where these letters are coming from. Okay, you can always stop the video and take a look if I go by too fast. It's better than being in class at least. So now we're going to give us 3 statements that start with statements. P is 10 is greater than 6. Q is 4 is greater than 8, and R is 3 is less than 5. Well, here's the deal. we don't need the whole truth statement for the truth table for this. They gave us 3 statements. They want to know the value of these 3 statements. So I established the truth value of each of them. Is 10 greater than 6? Yes, that's true. 4 greater than 8? Nope, that's false. 3 less than 5. Remember, this symbol points to the smaller one, so this is a less than. Left is less than right. And this is left is greater than right, just to remind you. 3 less than 5, that's true. So in a number line, 3 is to the left of 5. So if you drew a number line, you should be pointing to the number on the left. That's why Q is false. You're pointing 8 is to the right of 4. So I literally would replace P with a true or not Q. Now Q is false. So not Q is true. And I would evaluate that and I would get a true. And then I'm ANDing that with the value of R, which is true. So I'm going to get a true. They just show you that's just one row of the truth table. I don't even call that a truth table. I call that evaluating a compound statement. Okay, so we just did it a piece at a time. Now you could, if we had the whole, we did not make the truth table for this statement. I think we did one that was slightly different. Yes, we did. We had a not R. If we had done the whole truth table for this statement already, I would have just picked the row I was interested in. I wouldn't have to redo the problem. I would have already done it. But if you just have a single statement where you know the values, you don't have to do the whole truth table for that. That's my point here. Now we're going into conditional statements. Recall a conditional statement means P if then Q, means if P is true, then Q is true. That's all it means. It doesn't say if P is false, then Q is false. This is all this means. This is the only thing it promises. So a statement is considered true unless you can prove it false. So certainly this first one, P is true. If P is Q, then true is true is true. If P is Q, then Q is not, Q is false. That one's the only one that's false. If I don't know anything about P, if there wasn't, I say, if it is sunny out, we will go shopping. And it's not sunny out, but we do go shopping. Doesn't mean I lied. You don't know because it's raining out. That turns out to be true, and that turns out to be true. The only case of false is if you made the promise, that the first part of what you base the promise on, the basis of the conditional, or what they call the antecedent of the conditional, is true, but what you said would happen didn't happen. There are a number of examples you can use here, but if you study, what if I said to you, if you study for the test, then you will get an A. If you studied and got an A, that's fine. If you studied but you got a B or less, you say, well, that wasn't true. But if you didn't study, no matter what you got, that promise didn't apply to you, so you can't call me a liar. You have to say I was telling the truth. So this is the truth table for the conditional. And the order matters. That's the other thing to look at. This true-false is different than the false-true. You get a false here, but you get a true here. The other thing you have to notice, P then Q, if P is false, the whole thing is automatically true. You don't care what Q is. The only problem with this one being false is when the left is true. Think this is left, it doesn't even need to be in right. The left side is true and the right side is false is the only false. All other cases are true. So when P is false, when the left is false, so it's left, if left, then right, if you take the letters out of it. When the left side is false, left, then right is true. I don't care what the right is. It doesn't matter. So if you eat your vegetables at dinner, then you will get ice cream for dessert. This could sound like me talking to my grandson. So I made a promise. Now, if I eat my vegetables and I get ice cream, that's exactly what we expected to happen. If you eat your vegetables and you don't get ice cream, you say, hey, wait a minute, you said I'd get ice cream. And you say, say, keep your promise. But what if you leave your vegetables on your plate? You don't expect to get ice cream. That wasn't part of the deal. But if you get ice cream, you don't say, hey, you broke your promise. No, because the promise was based on this, so it has nothing to do with that. So the promise could still be true. So if you eat your vegetables and don't get ice cream is the only time you can call your parents or grandparents a liar. All the other times, if you don't eat your vegetables, consider it a bonus if you get ice cream, but they weren't lying. Okay? Here is the truth table for the if-then. This is the left side of the if-then. This is the right side. We were calling these P and Q earlier. If the left is true and the right is true, it's true. If the left is true and the right is false, this is our case where you have evidence of being told a lie. If the left side doesn't happen, there's no evidence of a lie because there's nothing to follow through on. So you have to assume the person was being truthful. So we talked about this already. It doesn't matter that if the first thing didn't happen, the second thing still does. So it's kind of like saying if the figure is a square, then it is a rectangle. So if it's not a square, then it is a rectangle. It's actually still true. Okay? Because there is the possibility that would be true. You could have an object that's not a square, but is a rectangle. And if it isn't a square and it isn't a rectangle, if they're both false, that's still a true statement. So that's the other way to look at it. The only time this would be false is if I actually had a square and I said, oh, this particular square with 4 equal sides here is not a rectangle. That's the only time this is a lie. Now, I can't turn this around. Just because something's a rectangle doesn't mean it's a square. The if-then, if Q then P, does not mean if P then Q. It's not the same. The left and the right matter. That's a big deal in this conditional. So what about constructing a truth table for this? So in this case, how many statements do I have? I see a P and I see a Q. That's a P, that's a Q. It doesn't matter that they're not. There's 2 statements. That means I have 4 rows. So we'll start. This truth table needs not P or Q. If not P or Q, then if P, then not Q. So there's a whole bunch of stuff here, and it seems complicated, but again, we break it down a step at a time. I already have a row for Q, so I make a not P column. I should say column. And then I find not P and Q. Not P and Q. Well, not P here this would be false, false, true, true. So I have an and statement here. So as soon as I see the left side is false, I know the whole thing is false. So those 2 are false because not P is false. True and a true is a true, and a true and a false is a false. Now, I've done that. That's this piece right here. Now I'm doing this piece over here. Notice I do this if then last. So if P, then not Q. So this is a left and this is a right. Not Q is on the right. So that's going to be false, true, false, true. So what's my left? My left is P. Whenever P is false, I know I automatically have a true on the if then. I can fill those in. Now, here on the first row, I have P is true, not Q is false. That's my problem. That's my false one. True, then a true is true. So now I've filled in this and this. And now, let me change my color. Sometimes I try to hurry and I get a little... This is my left and this is my right over here. It's nice that it's nice when they're in order. Sometimes I rewrite it just to put them in order. So whenever the left is false in an if then, my statement is automatically true. Now I have to look at the case where left is true. This has to be true. That's true. This is something called a tautology, or actually it's an implication. The fact that tautology, all true, but because it came from the final step as being an if-then, this makes it an implication. A final if-then that's all true is called an implication. So that would be some vocabulary to know. Now, this just goes through and finishes what we just did. You can stop this step at a time and look. And now we're going to move on to the biconditional. The biconditional statement means P if and only if Q. Examples of this are like, today is Tuesday only if tomorrow is Wednesday. If and only if. Those never happen out of order. Or tomorrow is Wednesday if and only if today is Tuesday. These go in both directions. So if it's false that today is Tuesday, it is also false that tomorrow is Wednesday. It turns out with the double arrow for the biconditional, a false if then a false is actually a true statement. Because what you're saying is these two things always happen the same way. They match. P and Q must match in order for this to be true. So let's take a look at the truth table for the biconditional. So what the biconditional is an anding of if P then Q and if Q then P, because the order makes a difference. So if P then Q is this true, false, true, true. But if Q then P, Q is now on the left. So left on the true. So this would be a true, true, true on the left, true on the left. This would be a false on the left, a true on the right. And that's okay. False on the left always gives you a true. This would be a true on the left for Q. False on the right. That's your false case. Notice these two switch when you switch the order and the if then. But when you and these two things together, these become the two truth cases. This is your if and only if. Notice when P and Q have the same value, it's true. When P and Q have different values, it's false. So that is the key to know for evaluating those. And let's try one. So again, we have a compound statement. This only has 2 letters, so I only need the 4 rows. There's my standard input columns for 4 rows. Looks like I want a not P and Q, so I find a column for not P. You can always stop the video and take a look to make sure you understand where these came from. And then I do not P and Q, and I get false, false, true, false. So then here, I'm using the not P and Q along with P. This is the left side, and left and right doesn't matter because this works in both directions. Only the single directional arrow, left and right, matter. I need to see that these are the same in order to get true. They're different in the top row. They're different in the second row. They're different in the third row. So because they're different, I'm writing a false. So I get a false, if and only false, that's actually a true. Students have a hard time with that because there's no truths to be seen here, but they match. They're the same, so it produces a true. That is an example of a compound statement with a biconditional. Okay, and that turns out it's the same as not and, but that's another story for another day. Now, here's another one. I do this biconditional list. I work in these parentheses. This time, though, I have PQR, and they actually did not do this correctly because what they did here was a little different. I would have done this whole truth table differently. I would have done PQR. There we go. This is what we're trying to do. So here was our statement, not P, if and only if Q then R. That's the statement we're trying to show. Notice I have 3 statements, so I have 1, 2, 3, 4, 5, 6, 7, 8 rows. So I'm going to do a not P. I got to do inside these parentheses, and this happens last. Negations go first, inside parentheses go next, and anything left, particularly if thens or if and only ifs, are last. Not P is here. Hopefully by now you're catching it. Now Q then R. Q is on the left, R is on the right. That's handy. So anytime Q, so I true and true is true. If true, then false. There's my false. There's a false there. When Q is false, these are automatically true. So I can actually go and fill those in without doing the rest. And then I look, true then true is true. True then false is false. So you can fill those in using the rules for if left then right. Q is on the left, R is on the right. Then I'm looking to see if this column and this column match to get a value of true. So false, true gives false. False, false gives a true because these match. Okay. Again, different, different, same. So they match. These match. It doesn't matter whether they match being true or match being false. If the left side and the right side of the double-sided arrow, the biconditional, are the same value, whether it's true or false, then the output is true. Here, if they're different, the output is false. Here they're the same again, and they're the same again here. So you get true and true there. So all the ones that are true are where the values are the same. Notice it doesn't matter if they're the same false or the same true, as long as they're both the same. So here's another idea of a self-contradiction. If I say P and not P, I get entirely false. So some books just call that a contradiction. The statement can never be true, so it's silly. That's just a vocabulary piece. And this is called a tautology. We talked about that a moment ago, because all are true. P or not P. You only need one to be true for the whole statement to be true. And if you're taking opposite values, one of them is always going to be true. So that's called a tautology. Should have made this 2 videos. This goes on for a while. So I am going to make this a second video. We're going to stop here and go back and talk about contradictions, implications, and tautologies in part 2 of this video. Thank you for joining.